We've been talking about derivatives in terms of limits. So we have some function. We want to find the slope of the tangent line that meets this function at exactly one point. We'll call that slope the derivative of the function at that point. But so far, we've been calculating this using limits of the difference quotient. I don't want to be using limits every single time I calculate a derivative. So we're going to have some formulas as a shortcut. And every single time we see a function like the ones in my talk today, we can just immediately know what their derivative is based on these differentiation rules. So let's focus first on polynomials. We'll get to exponentials later on. The easiest polynomial function is one that's just a constant. F of x equals c. If I was going to graph it, I just say y equals a constant. Maybe this is the constant c equals 10. There's no scale here, so I can't really tell. But I can see that, well, this is just a nice linear function, a function with slope 0. So its derivative, f prime of x, must be 0. Now, notice that this matches exactly with what I was saying about differentials last week, my idealized point of view, where if I could take infinitely small pieces of my functions, I would, but I can't. So this is our first differentiation rule, that the derivative of a constant is equal to 0. Now, if we wanted to, we could calculate this from the limit-based definition. I'd be taking the limit as h goes to 0 of c, the constant, minus c, the same constant, all divided by h, but my numerator is just equal to 0. 0 divided by h is still 0, so my limit must be equal to 0. So, like I was saying, my derivative of the constant function is 0. And using my differential operator, I can say d on dx applied to c is 0. Nice, easy. Let's pick something a little bit more complicated. So let's say instead we have f of x equals a power of x. So I'd call this a power function. Here, I've got x to the power n, and n is a positive integer. Well, probably the easiest one of these would be x to the power 1. Again, that's just a line. So I can calculate its slope directly. This will have slope equal to 1. Now, I like my easy examples. I like being able to calculate these things without actually going to limits. But we are going to move on to functions that are more complicated than straight lines. So what have we got so far is that my d on dx operator applied to the function x gives me exactly 1. And again, we can calculate this based on a limit. And if we think back to previous homework problems, then we've already seen things like the derivative of x squared is equal to 2x. The derivative of x cubed is equal to 3x squared. These should be familiar things. So let us come up with a rule for all of the power functions, no matter what power n is representing. Let's see what happens for taking x to the 4th power. My f prime of x is equal to the limit of my difference quotient. H is going to 0, and I have quantity x plus h to the 4th minus x to the 4th, all on h. So I have to FOIL this out very carefully. I get a degree 4 polynomial, or a quartic polynomial if you like vocabulary today. But after cancellation of my x to the 4th and my negative x to the 4th, everything left has at least one h in it. I'll factor out those h's, and I can cancel with the h in the denominator. What is left but 4x cubed? Okay, I think I'm starting to see a pattern here.